Hello and welcome to another special episode on the Total Space Network. I'm Mikko and today Rogue Space is back to chat with us. If you haven't seen the first episode where we talk about the company, Orbots among other things, remember to watch that after this one. And in short, Rogue Space is engineering first generation of orbital robots or Orbots. And joining me today are...
Hi, I'm Astro Rody. You might know me from some of our launch streams.
I'm Rich LB from Becoming Multiplanetary. You've probably seen me before on a few of the other episodes. Great to be here today.
I'm another space nut and I plan to die on Mars.
And of course, joining us from Rogue Space are the CEO, Jeremy Grimmett. How are you doing?
I'm doing great, and I brought with me today Rob McPherson and Gael Gertera, two of our engineers and orbital mechanics. So happy to have them with us. That way you're just not getting it all from me.
Awesome. And maybe first I would like to hear from Rob and Gail. What do you do specifically?
I guess I could start. So I'm a robotics engineer. I'm part of the planning for the perception, specifically the perception of the LoRa 1 mission, and some of the other tasks such as creating a robotic architecture, both specifically a software architecture that's going to use machine learning, commonly known as AI, as a buzzword, but it's really machine learning and data science.
And I work as the astrodynamicist for Rogue. I work on all the orbital mechanics problems that so we can do the mission planning of where we're coming from, where we're going, and specifically how to get there. I'm also working with a team to work on a software to help us do that in a bit of a new and innovative way for the field.
Yeah, we actually just completed our MOU with them. I literally just closed the press release, and we're going to be sending that out today or tomorrow. But, since we've talked, we've made lots of progress. We've expanded up the team. We've brought in Gael. We've brought in Rob. We've got a pretty hefty sales pipeline. We're working with Space Force on their new active debris removal OSAM initiative called Orbital Prime. We've put in debris removal proposals. We've got our compute has gotten submitted for prototyping because we have a compute module. So we had to, we submitted that up for prototyping. Golly, we've done a lot. We've got the architecture worked out for the autonomy. We've got, I don't know, man, we've done a lot. Rob's done a lot of mission simulation work. I've been a giant pain in his rear end, continuously nonstop changing targets and figuring out launch vehicles. And I think
I've been explaining to him why physics says no to him a lot of the time.
Yeah, I know, right? And I think Gael, I'm surprised his brain hasn't melted over the problems that we've had to ask them to try and solve. So he's these guys have really driven us to a whole other level, moving very fast. So super proud of them, and don't think I could ask for better
Fantastic.
people. I mean, right now we're right around 30 people right now. So I'm not sure I think we might have been at, 15 or 20. Now we're at like 30, I think. I'm really not sure, to be honest with you. There are new people that kind of show up and I don't even know. So right. As I explained to you guys before, we're really trying to build a community here at Rogue Space. And one of those things, there's going to be a need for additional personnel. We are hiring. We are looking for people. We're always looking to try and interview and try and find new people that want to try and pick up projects and things like that. But I think we're probably going to max out around 40 or 50 by the end of next year. We're probably going to need to add once funding, which is going pretty well right now. Once full funding is in place, I'd say we'll probably get to about 40 by first quarter of next year. So it's going to be a pretty heavy lift. Well, it's not here yet, but things are looking good. I'll put it to you like that. It has been quite a bit of work. I literally sent 75 emails so far today. Yeah, we have a few commitments right now from some investors, which is fantastic news. We didn't have those 2 weeks ago, but we have some commitments, and we have our first revenues coming in by the end of the year. So financially, we're looking really good. Totally bootstrapped on our own, and it's pretty amazing. So presently, we're raising an $8 million round. That's what we're raising right now. This is our seed round, if you want to kind of term it to something. The average investor or the guy off the street, so to speak. If they are interested, we're going to be putting out a crowd fund on Net Capital over the course of the next, hopefully, 2 or 3 weeks. We're almost done with all the stuff. We've been pretty held up trying to get some other little pieces worked out, but we've decided to go ahead and do one more little fund round, one more fundraising effort over on Net Capital, so they'll be able to do that. No, people from around the world will be able to do it. There is some anti-money laundering checks that have to be done, but the platform handles all that fun stuff. The escrow company handles all that, so.
I think Gael's probably the best person to aim this question at. I had visions of Orbots grouping together as almost like an on-orbit transformer. Is that something that the machine learning will eventually aim to do? Like have them connect together as one bigger module and do multiple tasks at the same time, like a giant Zord from Power Rangers almost.
So yeah, I wouldn't think so in the near future. However, as a long term, why not, right? But for the short term, it's we want to do automatic, especially the perception side is mostly computer vision oriented and more precise maneuvering, right? So that's essentially kind of the near term goal. So just think of it almost like a drone, but in space, right? So nowadays there's these really fancy drones like the Skydio and the DJIs, right, that have automatic like object avoidance, right? So that's kind of our near-term goal. But yeah, I think the future, especially with the aerospace industry, you never know, right? So there's these companies that have, for example, creating commercial space stations as their goals, right? And those will need to be serviced as well, right? Not just space debris, but space. We're in an exciting time where space is really just a new frontier. So. Yeah, but as far as the swarming, since they're already implemented in drones currently, that can definitely be a possibility for maybe larger inspection or larger perception type of tasks, right? But since they can be done on drones on Earth, right, why not in orbit as well? So.
You'd be amazed at what we can get done through simulation. Like one of the people that we work with quite a bit, Kev Carrico, he can drop everything into a 3D engine, a video game engine. And believe it or not, that's what we use. We're using video game engines to do some of the simulation. So, for example, a few months back, he dropped Lara into an environment where all the position of the different cameras were put into place, and then we were able to see from the perspective of Lara what that vision matrix was. So we're able to do quite a bit in simulation to see how it's going to work. Now, to take it a step further, whenever you get to the actual nitty-gritty, like the electronics and things, we're working with Draper, which is a big R&D outfit out of Boston, who's the result of MIT. It's Draper Labs, and we're taking on a model-based engineering platform with them. So there's quite a bit that we can do right here on Earth in a simulation environment that helps us accelerate the development. But as far as gnarly problems and weird things that happen or that you have to get done to get something moving in space, that's definitely a Rob question. Lord knows I've probably given him enough problems. So
the software that I use to do most of my simulations is Systems Toolkit or Satellite Toolkit, STK, and it's phenomenal at doing some real world simulation. So I do a lot of calculations. I'm a little bit old school. I still have my TI graphing calculator here that I do a lot of my orbital calculations with before I toss it into anything else. So I can work out where I think something's going to go, the angle that we have to thrust at, and then when I toss it into STK, it adds a lot of the physics and the reality that goes back to the old joke that physicists like to work in frictionless, airless vacuums, and that's not how it works in the real world, even when we're talking about space. So it does a great job of doing that, and so I'll calculate. Let's just say it's like, oh, okay, so this will take me 50 meters per second of delta V to do this maneuver, and I toss it into STK, and it's like, nope, that's actually going to take you 63 and a half, or whatever along those lines. And so what it's preparing me for there is when we get Laura 1 up, one of the first things that we're going to be working on is figuring out how calibrated our actual thrusters are to what we think they're going to be. So we're going to tell it to point in this direction and thrust. And then we're going to have to record it a little while later and see, okay, did you actually push me in the direction I told you to? Or are we 2 degrees off in one of the directions, or 4 degrees off? Or maybe you're thrusting at 3% less thrust than I told you to, just because of, again, real world physics. So STK does a good job of simulating a lot of the little nitty-gritty calculus details that I don't necessarily get into in my back-of-the-envelope calculations. So it's preparing me even further for okay, now we have to take into account that there's some imperfections in the actual manufacturing that are going to affect our calculations as well.
Yeah, and so from a machine learning perspective, I think the words that Jeremy was looking for is digital twin. Right. So digital twins are essentially how robots are developed. Right. So Tesla develops their self-driving technology in digital twins. Right. And so the game engine that is most commonly used with the robot operating system is Unity. Right. So there's either Unity or Unreal. Right. And so the whole point there is, again, try to recreate the space environment, but, using some form of, really real, close to real life graphics to train your machine learning models for whatever purposes they would be. So NVIDIA has actually quite a lot of simulators that are close to real life, like the NVIDIA Isaac Ross, right? There's a bunch of them out there. And so, we've done our research into how our robots developed for self-driving cars, for some of the you can say aerial robotics, such as drones, right? And so it's just the same methodologies, but we'll be applying that to space systems.
I think that's just kind of the nature of a technological industry, is that we're always taking inspiration from each other, and it's not necessarily even conscious at all times.
Yeah, I think Rob's right. I mean, there's plenty of times where it's an email or a web page, or somebody sends over a YouTube or something like that. I'll give you a great example. The other day, one of our investors sent me a link to this article that got published by Jake Abbott at University of Utah, and he is using magnets or magnetism to control non-ferrous objects. Okay, so you can have an aluminum or copper ball or whatever, and magnetism, the magnetic field, actually still affects that object. Now, if you take that and put that into space, that's interesting. Because if you can use one of the big problems that we have in space is that you have this object, okay? It's not just flying just like this, especially if it's a piece of space debris. It's not just flying up there. It's doing this number. It's tumbling, it's moving, it's doing all kinds of things, okay? So it's flipping around on all three axes. And then it's moving through space. So what if we were able to catch up with it and use that technology to slowly stop that tumble? What if we were able to get it to slow down so that our arms could then reach out and grab a hold of it? That's a thing. And so one of the meetings we have today is actually with University of Utah to, start working on that. So it's really powerful stuff. It's really amazing people coming up with these different little ideas that we can go latch on to, whether it's a university or whether it's, iRobot or, Boston Dynamics making some robots dance. You just never know where it's going to come from.
Yeah, it's when you started talking about magnets, I'm instantly thinking about amusement park rides. A lot of roller coasters will use magnets to help control acceleration and deceleration before they actually get to a braking system. So, and they'll just have like two really powerful magnets and then like a fin made of copper or aluminum or brass or bronze or a series of different changing materials in order to just use the resistance between the magnets to slow it down or change its behavior while it's approaching the actual brake pads, just to ease the braking process and avoid people getting hurt. So yeah, there's some fantastic things that can be done with magnets.
Yeah, the problem that we have in space is a lack of power. And typically you need some pretty powerful electromagnets to do some of these things. But here on Earth, it's a little bit easier. Up in space, you're limited to that power.
Absolutely.
I was also thinking about this dampening field that you were talking about and thinking, well, if it's tumbling along three axes in space and for whatever reason this field becomes active and starts to slow it down on one axis, then you're gonna start having almost like an imbalance of force. So it's going to start going off trajectory if it slows down on one axis but not the other. So not only are you going to have to compensate for that, but, by moving this field with it, if it goes off axis. This is, I'm just even mulling it over in my head. It's infinitely complex.
That is why we have brilliant computer vision technologists like Gael, and that's why we have brilliant orbital mechanics like Rob to help us figure out how to properly position and then move things around so that we can distribute that field appropriately. Mm-hmm. And that's why we're going to work with University of Utah to try and refine some of that. So, thus the research and development and the bleeding edge of space debris removal technology.
And the great thing about this is if you're able to do it in this method, then you don't require companies to throw on a like mag plate onto their satellite or anything like that. This will work for anything out there right now. You know?
Yeah.
So,
and if you have a big enough power system and a big enough set of armatures, you would be able to do the same thing for a much larger satellite. Swarm those guys together and have them cooperate to stop the detumble of a much larger system, several hundreds of kilograms. That's a thing. That is a very real thing that's possible in the future, like Gael said. But right now, we got to start off with some little things.
It's along the lines of what we're going to have to figure out, because much of the debris up there, it doesn't have any of those mag plates, because until, maybe 5 years ago, nobody was even talking about this.
That's right.
It was talked about in academic circles, but nobody was actually doing it.
And you can't guarantee that the piece of debris is even ferrous in nature.
That's right.
From the information I've gotten on it so far, I believe so, yes. That's definitely something we're going to have to talk about and develop more in the future, though. I can't say with 100% certainty, but it does seem like it would be a possibility.
Yeah, it's going to require different technologies. It's going to require a combination of different technologies to accomplish one end goal. Because and I think that's one of the big differentiators for Rogue, is that we don't believe that there is an end-all, be-all solution for absolutely all of the problems. That I think that's pretty ludicrous to believe. We believe that it's a combination of technologies, a combination of methods, a combination of systems and disciplines that would ultimately help us remove that smaller debris.
A lot of the systems I've been seeing so far being demonstrated are exactly what they're talking about in terms of like a mag plate or something on it that you can connect to. But I can say just from experience of the targets we're researching, there's a few of them that are in 200 pieces at this point. So that means we can capture exactly one of those with that method, if we're lucky and that mag plate is not its own piece of debris from the impact or the explosion or whatever caused it.
The technology that Dr. Abbott put out there is more about controlling the spin of the object in order to allow us to then go capture it. So step one actually is to approach it. That's where Gael comes in, and Rob. Then we have to maneuver around it. That's where Rob starts coming in coordination with Gael's work. Then we have to take a technology to actually get control of that object and put it into a position where we are then able to attach it. That's a different technology. Then we got to be able to hold on to it, okay, or store it. That's a different set of problems. So every single step is going to require a different piece, a different discipline. It's all about bringing a team together, a group of technologies. I think that's a big advantage that we have.